Alright, hey, today we are talking about ocean water chemistry and patterns that we see with ocean water. And I'm sure everyone is aware of this, but the ocean, it's salty. It's salt water. But what does that really mean to be salt water? It just means that there are some dissolved minerals in that water. And the ocean really doesn't have that many of these dissolved minerals. It's around 3.5% dissolved minerals. And most of those dissolved minerals are sodium and chlorine, which are just table salt. It's the stuff that we put on our french fries, but there are many other dissolved elements in the ocean, and we call all of them collectively, we call them salts. We measure these dissolved minerals in salinity, and the unit of measurement here is parts per thousand, so 0/00 parts per thousand. And this just simply means if we randomly sample 1,000 molecules from the ocean, the majority of them would be H2O, but somewhere around 35 of these molecules would be our salts, mainly sodium and chlorine, but some other ones in there as well. So the ocean is considered to be around 35 parts per thousand. But one of the big questions that we don't think about a lot is, why is the ocean salty? Where did that salt come from? And there's really two main sources of sea salt. One of them is just chemical weathering of the continents. We talked about that dissolved load of a river, dissolved elements flowing in all rivers that end up flowing into the ocean. So over time, these dissolved elements are brought to the ocean where they collect and build up to, the saltiness of the ocean, 35 parts per thousand. Another source of salt is actually Earth's interior, and I'm talking about volcanic eruptions on the ocean floor. A huge part of volcanic eruptions is actually gas. So some of those gases get dissolved in the water, and that adds to the salinity of the ocean. But if we keep having rivers full of dissolved minerals flowing into the ocean, why doesn't the ocean just continue to get saltier and saltier? And that's just simply because of equilibrium. At the same rate those dissolved minerals are added to the ocean, they're also being removed through the precipitation of those minerals into rock layers. So the ocean sits around 35 parts per thousand, but there is some fluctuation. It could be somewhere between 33 to 38 parts per thousand. But what really is the cause of that range, that changing salinity in the ocean? One way that we can increase the salinity of the ocean is by removing fresh water. And yes, we can do this through evaporation, so places that are warm have higher rates of evaporation. We can make the ocean saltier that way. But one of the key ways we can make the ocean more salty is by removal of fresh water when we form ice. So when we form sea ice in areas that are cold, the poles, north and south, that ice is mainly H2O. There's bonds between the water molecules, and there's really not a lot of salt that gets trapped in there. So we're removing the fresh water producing ice, and the salts that remains in the liquid water left behind. So that water is actually saltier, has more salt in the polar regions than we do other parts of the ocean. And when we want to decrease salinity, all we have to do is add fresh water. So that might be through runoff or precipitation, but again, like we were just talking about, a lot of it is dealing with ice. And when we melt these massive chunks of ice floating in the ocean, that's adding large quantities of fresh water to an area. And when we add that fresh water, it means that we're diluting the seawater and it's less salty. So hopefully you're kind of picking up on something here, that this variation in the ocean is actually pretty closely tied to our seasons. Where in winter, we're removing fresh water, making it more salty, but in the summer, we melt that freshwater ice and we make the ocean less salty, decreasing the salinity. Moving on from salinity, we're going to talk about a few patterns that we see with the ocean. And really, we're specifically looking at both temperature and density of water. And when we look at temperature, we're just looking at temperature variation with the depth in the ocean. So how does the temperature change from the surface to the bottom of the ocean? And places at like the equator or low latitudes, it's exactly what you would think. The surface water at the equator is very warm, like that's why we go there for vacation. But very quickly, it changes from warm water to near freezing water in this area called the thermocline. A thermocline is just an area of rapid temperature change between 300 and 1,000 meters deep. And if I give you enough time, you would probably come up with the reason why this thermocline is present. What's happening between 300 and 1,000 meters deep in the ocean? And if you guess that sunlight is getting less and less strong, you're right, that's it. Sunlight is being filtered out by the depth of the ocean, where at 300 meters there's still some sunlight, but then it starts to fade very rapidly underneath 300 meters until we get to 1,000 meters where there's almost no sunlight, and that's why it's going to be very cold. When we get to high latitudes or close to the poles, again, doesn't take a lot of thinking to figure this out. The surface water at the poles is freezing. Could you guess that? It's cold. And then that temperature stays the same from the very top of the ocean surface to the very bottom of the ocean. So there's no thermocline present at all. The next pattern we're going to look at is with density. And first of all, I feel like we should just define what density means. Density is defined as mass per volume. So if we can add more molecules, more stuff in the same space, the same volume, we're going to be increasing the density. And there's two ways that we can increase the density of salt water. The first way is through the salinity, the salt themselves. Because when we dissolve these salts in water, we're adding actually like physical molecules, we're adding material to the water, meaning there's a greater mass. All of those molecules, they have mass, and we're not changing the volume at all, we're just adding more elements, more things into the water. And because we're adding more stuff to the water, it's going to increase the weight. The other way to increase density is through temperature. When we have cold water means the spacing of the molecules is much closer together. So cold water means we can pack more molecules into the same space, and because we have more molecules, it means there's a higher density, there's a higher mass. So when you think about density changes in the ocean, make sure you're thinking about salinity and also temperature. Moving on to our patterns with density, at low latitudes like the equator, the density of the surface water is very low. Low density water likes to go to the top. The higher density water will go to the bottom. And there's a transition zone here again, this time called the pycnocline, between 300 and 1,000 meters, where the density goes from very low to being very high. And that change in density is really just tied to temperature. We know that the thermocline, the same area, 300 to 1,000 meters, is where water starts to get very cold. So as it becomes more cold, it also increases the density. The pycnocline is really important because this layer ends up separating the surface water from deep water. Just like how oil and water don't mix, surface water and deep water will not mix either, because of this density difference, because of the pycnocline. Very important. When we get to the poles, we see a completely different pattern. Again, surface water at the poles is cold, and cold means it's going to have a high density. And so that temperature and the density stays the same from the surface all the way to the bottom of the ocean floor. There's no pycnocline here, so this is where water is actually allowed to mix vertically. Surface water and deep water are all the same density, so it can be stirred up and down in these areas. And to wrap up our notes for today, we just have to talk about the 3 different zones that make up our ocean. Starting with the top of the ocean, working our way down, we have the surface zone, which is also sometimes called the mix zone, and then it's also called the surface mix zone, so just make sure you know that. And the surface zone, or the mix zone, is where the surface water is being mixed up by wave action, and it's also going to be warm because we're getting a lot of sunlight here. Below that surface zone, we have the transition zone. And this is where we're having transitions of temperature and density. And I'm talking about the thermocline and the pycnocline. They would be located in the transition zone. So this is somewhere between 300 and 1,000 meters deep in the ocean. After the transition zone, we just have the deep zone. Deep zone water, deep ocean water, it's all going to have the same characteristics. It's going to be cold, and it's going to be salty, and it's going to have a high density. And you're probably looking at that diagram and seeing this deep zone water actually at the surface the closer you get to the poles. And again, that's because this deep zone water, it's not necessarily about the location, it's really talking about characteristics. And yes, at the poles, when you get close to the North and South Pole, it's going to be deep zone water at the surface. It's going to be cold and salty and dense from the top to the bottom. That wraps up our notes for today. Kind of some heavy stuff here with density and salinity. Please make sure you're reviewing your notes, and if any of this didn't make sense, please make sure we're asking questions. Okay, otherwise, see you later.